In this session, we will discuss about the closure properties of the regular languages. Previous, we have seen about the finite automata with output like Mealy machine and the Moore machine. Next, we have seen the regular expressions. So we have converted our finite automata to the regular expression using the Arden's theorem. And also we have seen how the regular expression will convert into the finite automata. Now we have the closure properties of the regular languages. That what will accept the properties of regular languages. Like we have union, intersection, difference, concatenation, clean closure, reversal, homomorphism, inverse homomorphism. All these are the closure properties of the regular languages. We will see it one by one how it will accept these closure properties. So the closure property, that means we have certain operations on the languages here. So when we applied on these languages, so the result will be the same, the regular language. Here, for suppose we have the regular languages, we can use any representation to prove it as a closure property. Here we have taken L and M are the two regular languages. The regular languages that accepts the union. So because it has the closure property of the union, that is L union M. When we apply the union operation, the L and M regular languages, L union M is also the regular language. That means we have R and S both have the regular expressions. So that define the regular expression that R is the on M and S is the regular language of M. Then R plus S, that is a regular expression. The regular language that we call it as L union M. For the regular expression, the language is the L. For the regular expression S, we have the language is M. Whenever we apply R plus S, the union operation, the L union M is also the closure property of the union operation. Therefore, so we can see that regular language is closed under the union. And also closure under the concatenation and the clean closure also. So whenever we have the RS is a regular expression, the language is LM. That means we have two regular expressions R and S. The regular expression of R is L. The regular expression for S is M. When you apply the concatenation, that is R into S, the language is nothing but L into M. When we apply the union that we have seen that R plus S, the regular language is L union M. The same concatenation, that is R into S, so the language is L into M. Here that means we are applying the dot operation, that is the concatenation. So therefore the LM is also a regular language. Next, R star is the clean closure operation. That is whenever we have the R star is a regular expression, the language of R star, the clean closure of the regular expression for the language is L star. The regular language of the clean closure is L star. Therefore, L star is also the regular. So whenever we have under the intersection, so whenever we have L and M are the two regular expressions, the L intersection M is also the regular. So we will see the proof. We are saying that L union M is regular, L into S is the regular, L star is the regular. We will see the according to the proof. Here we have seen the intersection property. Just check it carefully. Here we have the two DFAs. A and B are the two DFAs. So the languages of the DFA is L and M. Whenever we are constructing the language of the DFAs of A and B, the states of the another, that is the distinct pairs of the A and B, and also we have to take the start state, and also we have to take the transition state. Based on this, we have to define which language it is accepting, the DFA is accepting which language. First, we have to check which language is accepting the DFA, and we have to go with the intersection property. For that, we have taken the two A and B, two DFAs. and we are identifying it is accepting which language. So we have to make the accepting states, and we have to check the pairs of the accepting states of both A and B. We will see the example here. Here I have taken two DFAs, 1 and 2. So here we have taken the two states, A is the initial state and B is the final state. In another DFA, we have taken C is the final state and D is the intermediate state. So here C is also the initial state. Whenever we apply the intersection operation, so we have to merge these two, right? Two DFAs. So the states we will get it as A comma C and A comma D, B comma C, B comma D. That means, so to apply this, so A comma C, A comma D, B comma C, B comma D. So here, so A comma C, when we measure this operation of A comma C, so first we will take the transitions from A and we will take the transition from the C. Here from A we have the 0, from A we have the 0 to A itself, so we have A, so we have given to this state, and from A we have the B transition on input alphabet 1, on A on input alphabet 1 we have the B transition, from B again we have A, from B again we have A, and on 0 transition as well as the 1 transition. So from B we have the 0 transition as well as the 1 transitions. So when we apply the concatenation operation, so again we have to check with the B operation with the BC and BD. So we are taking the B on input alphabet 0 and 1, B on input alphabet 0, that is A, and 1 to B, and to B. So next we have the C and D. So whenever we apply this, so that we have AC, AD, BC, BD. Whenever we are doing the intersection operation, you should not leave any state. So on C we have the input alphabet 1, on C input alphabet 1, on C to C input alphabet 1, and also on C to D, on C to D, C to D we have the 0. And also we have the 0 initial state D to D itself. So here we have D and D, 0 state, and D to C. So we have to take D to C, we have 1 transition. First let us observe. We have seen the transitions. First we have to define the both DFAs, that is accepting the which language. Here when you see here, from A that is starting with the 0 and ending with 1. If you start here, this is the initial state and the final state. So we have the 1. So the same thing that we have to check it once. On A, so it is going to 0, and we are making it as the final state, because whenever we are doing this B, B is the final state here. So B is the final state here and C is the final state here. But we are making B and D as the common, after intersection we are making B comma D is the so here we have seen closure properties of union, concatenation, intersection. So here, so B and C as the final state. So B comma C is the final state. So next we will take the DFA, that is accepting by both DFA of L and M. Here the language we have taken it as the L, and for the second DFA we have taken it as the M. The DFA that defines L intersection M, so that we have to check the language, which is the regular one. So that means to check these we have to take the DFAs for union or the intersection or anything. First we have to take the DFA, and we have to check which language it is accepting, and we have to combine both for the union, and we have to take the common for the intersection, and we have to check the language is the under the regular language or not. Same like that we have closure property of the difference. So here we have taken L and M are the regular languages. When you apply the difference, that means we have to take the result as if the string is in L but not in M. That means here whenever we have the L and M are the two regular languages, then we will get the difference as L minus M. So we will see the proof. First we will take the DFA of A and B, and we have to make the difference. So that means, so we will see the example of L minus M. Here the same example that we have taken. Whenever we have the intersection, we have taken AC, AD, BC, BD. Same for the difference. We have to check the L that is in L and difference means that is minus M. So here simply you can observe this B and C are the final state. The difference that we will get it as the another one, right? So now the B comma D as the final state, that is not the C. Whenever we apply the difference, the transitions that was to be, that is the language of L, that is not in the M, right? So the language it is L, it is M. So it accepting the L, that is not in M. So 0 and so we have the 1 that is accepting. So whatever the C and D that we have, so C and D that we have 0. So whenever we are taking the transitions are the same. So that means whenever we have the L minus M, here the language is empty in this case. So there is no language because, so here the language we have L and we have the M. So here we are doing the difference L minus M, right? So here the language is empty in this case. That means there is no language that we are constructing in the L minus M. But the language that we will take it as the regular language. So that means when you take the DFA, that is we will get it as the empty in this case. Whenever we have the complement operation, complement means, so when we take the any language with respect to alphabet, summation, so that complementation means the reverse, that is summation star minus L. The language we have to take the minus L. So that is the complement operation. So whenever we have the regular language of summation star is a regular. The regular because the difference of regular language is also regular that we have seen in the last. So we can say that complement is also the regular. And the reversal operation. So whenever we take the language L, the L power R, that means the set of strings that we have taken, those things are also the reversal, those are also the regular. So here we have taken the strings 0, 0, 1, 1, 0, 0, L power R. So that means the reversal we will get 0 as 0, 0, 1 reversal means 1, 0, 1, 0, 0, the reversal means 0, 0, 1. If you see this the proof of this reversal operation, first we will take the regular expression of the L and we have to do the reverse. That means we have to go with the L power R. So whenever we have E equals to F plus G, the reversal operation E power R equals to F power R plus G power R. Whenever we have the concatenation, that is F into G, the same thing E power R equals to G power R into F power R. So when you take the clean closure operation F star, the reversal operation of the F star is F power R whole star. So here we have seen, we will see the example like 1 star 0 plus 0 star 1. So let we have taken the expression of 0 1 star plus 1 0 star. So when you apply the reversal operation for this regular expression power R, so we have 0 1 star whole power R plus 1 0 star whole power R, that is according to the union rule. Next, take the concatenation rule, that is 1 star power R into 0 power R we will get, right? For this same expression we will get 0 star R into 1 power R, that is according to the concatenation rule. Next, apply the closure property, that means apply 1 power R whole star, that is 1 star itself, 0 power R, that is 0 itself. Next, 0 power R whole star, that is 0 star itself, and 1 as it is. 1 power R means 1 itself. Next, apply the closure rule. So when you see this 0 1 star plus 1 0 star, we have get the reversal right 1 star 0 and 0 star 1. That means we have taken the expression as E and we have received the E power R. So that means it is the closed under the reversal operation also. Next we have the homomorphism. So whenever we take the alphabet is a function, so we have to assign some strings to every symbol, right? So that is in the alphabet or the any digits. Example, we have the 0, 1. And also you can define this h of 0, that is homomorphism of 0. We have taken AB and 1 we have taken it as the epsilon. So we have to extend the strings based on the alphabets. We can extend up to A1 to any number, right? AN. So the homomorphism, when you apply this h of A1 to h of AN. So for example, so we have taken A0, 1, 0, 1, 0. So we have taken 0 as A, 1B, A, AB. So like that. So the homomorphism of a language that is formed applying to every string in the language. So we will see the proof how it is closed under the homomorphism. So we have taken a string that is W, that is h of W, that is in the language L, that is in the regular language. So if you see, E is the regular expression and the language is the h of L. H of 0 is the AB, and we see the regular language of the expression 0, 1 star plus 1, 0 whole star, right? So based on that, you can simplify that it is the homomorphism. Simplify this. Epsilon star equals to epsilon AB epsilon star plus epsilon of AB whole star. Check it carefully. We have the identity under concatenation. AB epsilon star epsilon of AB whole star. Epsilon star is epsilon itself, and AB whole star, that is AB whole star. So when you contain AB whole star, that is in the h of L, so it is regular under the homomorphism. Next, inverse homomorphism. Whenever we have a string W, H inverse of W, that is the reverse homomorphism, is also under the closure property. So if you see H inverse L, that is L power W dash, that is the H of W dash is in the regular language. See the example. So whenever we have H inverse L, any W with 2 zeros and any number with 2 ones, so that is the H of L, W is AB, AB. So if you see the proof here, we have any number of input alphabets and the symbols. The H inverse of L will take it as the regular language. That means all these are the closure properties like union, intersection, closure, homomorphism, inverse homomorphism. All these are the closure properties of the regular language.